don't click the record tab because it's, yeah, I don't know. It's scary. If you turn it off, we can't get the recording later. And it's easy to accidentally hit, and it makes it, yeah, anyway, they need to fix that. Anyway, I say that, then it might be better now. All right, so we have 5 more minutes per my clock. And then typically I'll have all of a 2-minute sort of intro thing, and then we'll get going.
Okay. How many people have we got?
Right now, we have 26, including us. There are 40-something registered, and if the people that have joined would type something and click that tweet button, we can probably get more.
Takes this thing ages to convert files. So can everybody hear us right now, or is this just you and me talking?
They can hear us.
Hello, everybody.
And now we can see your slides.
Oh, good. I'm glad somebody can. Oh, there we go. No, I can. I'm just going to. Okay. Just checking that everything works. So the only 2 images I see are me and you.
Yeah, so the webcams and microphones are not enabled for everyone. I did briefly earlier just to see what it would be like, and nobody joined anyway. But
okay.
But anyway, I think that with this many people on, I've never had like 4 people in a video chat where there wasn't some ridiculous audio thing going on. So yeah.
Okay. Right, that works.
Nicholas is raising hand. I'm willing to bet that hand icon kind of got the better of him. Curiosity on that thing is pretty fantastic. Or maybe Nicholas has a question.
If you have a question, Nicholas, go ahead and type it. Tell you what, if everybody who's on can hear me okay and is happy with what they're hearing, could you just type a smiley face in the text stream? Cool. If you can't, then type an unsmiley face. Great.
But if
Jean-Philippe Bernardi is here. Hello, Jean-Philippe. Count how many smileys we got. 1, 2, 3, 4, 6, 15.
probably had some conscientious objectors.
17, 18. Yep, 7.
Yeah. I respect that. Yeah, so I guess there's 2 minutes left. I can kind of talk about the interface a little bit before the sort of intro. So yeah, there is chat with everyone here in the white box on the right. You can see all the people. There's technically private chat, though it's not that useful in my experience in this scenario. We have live polls and Q&A. So if you have a question, the best thing to do is to post it in Q&A because it won't be competing with chat. And also there's like the ability to vote up and down and mark them answered, which makes it easy to manage them. So that is everyone's whirlwind tour of how Big Marker works. And I suppose I can go ahead and get started. So thanks everybody for coming. This is the second meetup for the remote chapter of Papers We Love. We're trying to do these every month, and I've really enjoyed the last one we did. We unfortunately lost the recording, but that shouldn't happen again. We know explicitly why we lost the recording, and it was foolishness on the part of someone mucking around in the server. We know his name. Anyway, so we're doing these every month, and we will be posting this final video on the Papers We Love YouTube channel. And I think we had the recording of this one. I think that was a different one I lost. Anyway, sorry. So Philip Wadler is with us. He's going to present the paper Definitional Interpreters for Higher Order Programming Languages. And I will go ahead and paste the links to the paper in, just so everyone can download it, follow along if they feel like it. And they're going to be kind of slammed together, but that's all right. And thanks to Papers We Love for accepting us as a chapter. The organization is really well run. It's really great to be a part of it, and I like what they do. And so if you don't know about Papers We Love, it's a repository of academic computer science papers and a community that loves reading them. Anyway, and Papers We Love Conf was awesome. So before we get started, I need to thank a few people that are sort of sponsoring the tech behind it. So Daily Drip is my startup, and I'm super grateful that I get to spend time basically working on community type stuff and trying to make programming better. And we provide daily continuing education content for developers, so you can feel free to check that out. RemoteMeetup.com is an open repository for meetups like this that operates very much like an open community, and Franze, who started it, has been extremely helpful every time I've done a remote meetup. We're getting better at all the technical and social hurdles that come from trying to run them, and so thanks, Franze. Hired.com sponsored the first BigMarker account for us with Remote Meetup, and they appear to be a fine company to check out if you're looking to hire technical talent. I have not used them to hire yet. And then BigMarker themselves stepped up and sponsored us with their Big Daddy plan. So we now can have up to 1,000 attendees at a given meetup. So if anyone was worried about tweeting because they thought there might not be enough space, we can handle it. Anyway, so I really enjoyed BigMarker for doing this sort of thing. I've tried a lot of things, and it, aside from the one time I lost a recording, has worked pretty fantastically. All right, so with that out of the way, we can begin the presentation. I mentioned before, but I'll mention it again, there's a Q&A tab. You can see it beside the chat tab. If you have a question, plop it in there. We'll get to it at Philip's leisure. And so with that, I will go ahead and step out of the way, turn off my camera and microphone, and let Philip have the stage. Thanks.
Okay, I'd like to thank Josh for inviting me to do this. I'd like to thank all of you for showing up. I've never done anything quite like this before, but I'm really grateful to have the opportunity to do something like this. Global warming is a serious problem. One of the major things that contributes to that is getting in an airplane and going someplace. So we're all going to have to get better at talking to each other and meeting virtually rather than physically. So the chance to get some experience with doing that is quite valuable to me. I'm really hoping, so I've been fortunate enough to give this talk before. I was invited to speak to Papers We Love London, so I'll be reprising that talk. Now, that was a talk in person, and one of the great things about talking in person is I can pause and look around the room and see if anybody looks puzzled. Is there a standard icon for I look puzzled? I don't know. Somebody knows what it is? Could they type it into the stream so I could see it? Nobody's typing anything. Just type I am puzzled. This is helpless. Everybody's expecting somebody else to do it,
Oh,
no, or nobody
so
can.
you might have to scroll down the chat. People are.
Oh, do I have to scroll down the chat? Is that the problem?
You don't normally, but if it wasn't.
There we go. There we go. It was perfect. Thanks, people. Now I see it. I see a puzzled-looking icon from lots of people, and one person typed, I am puzzled. That's great. So I can't just look around the room, so and somebody has these shrugged shoulders. So if you don't follow what I'm saying, I am sure there'll be somebody else in the room who also doesn't follow what I'm saying. So you will be doing yourself and them and me and the rest of the audience a great favor if you actually indicate your puzzlement. So I'm going to try to do this interactively. I might ask people to type in smileys from time to time if they're happy, and we'll see how that goes. So as I said, I'm new to this. I expect many of you are new to this, and we'll see how that proceeds. So yeah, I'm getting lots of feedback in the stream, which is great. Please just keep that up. Now I have to figure out how to go to the next page. Oh, there we go. So that's John Reynolds, possibly the greatest computer scientist never to win the Turing Award. He has done amazing things for the foundations of computing. And I'm going to tell you about my favorite paper of his. I'll explain a bit about the importance it had in my own life. I also want to say I'm really grateful to Papers We Love for existing. I think it's an amazing idea to say, hey, there are great papers out there, let's celebrate them. Understanding the history of the field and what's out there that's wonderful is fantastic. People love many papers written by John Reynolds, and they even love John Reynolds himself. There's actually a conference called HOPE, which used this as their advertising logo. So if you're chuckling or something, you can now type in smileys, I guess. So getting some nice feedback, which is great. Thank you for the positive feedback. So it wasn't difficult to pick John Reynolds' paper. I'm actually on record as this is one of my favorite papers. By the way, Josh, there's my website, which I circulated. The blog post I put up earlier today includes a link to my previous blog post that has all of the papers cited in this talk. And if you could put up a link to that, then people could go look at that later if they want to find any of these papers. So it wasn't, and one of the links you'll see there is to something I wrote about this particular paper many years ago, saying this is a great paper. Thanks. Is that the right one, the one with the references? Well, I'll hope so. Josh, is that a link that has about 10 different references on it if you follow it?
You know, it's not, and I thought it was when I pasted it, so I just didn't do that correctly. Super sorry. I'll find it and I'll paste it in. Sorry about that.
Brilliant, thanks. But let me go on. So I'm on record that this is my absolute favorite, but there are many others I could have picked, right? I've got lots of favorites. And so let me just review a couple of those in case you want to go looking at them later. John McCarthy, Towards a Mathematical Science of Computation. Peter Landon, The Next 700 Programming Languages. And Gordon Plotkin, Call by Name, Call by Value, and the Lambda Calculus. I guess I should say a word or two about why each of these is significant. McCarthy's paper is significant because it does exactly what it says on the label. It really was the first paper to say, hey, maybe we should treat programs as mathematical entities, and maybe we could prove properties of programs, prove that an optimizing compiler is actually an optimization of actually implements the languages defined, and that optimizations don't change the meaning. Peter Landon, The Next 700 Programming Languages. What he was actually saying there is we need lots of domain-specific languages. That's what the 700 programming languages were. And that perhaps the way to get these is by defining appropriate libraries for a functional programming language. So Lisp was very popular then. Peter Landon had his own functional programming language, ISWIM, which stood for If You See What I Mean. And this was the paper that described it. Among other things, this is the paper that introduced the notion of abstract syntax as something different from concrete syntax. It was also Peter Landon who introduced the idea of a virtual machine, the basis for things like the JVM. He introduced something called the SECD machine. So he's made many significant contributions. And among other things, in the SECD machine, he described this idea of a jump operator, which really confused me. It just looked like a hack added to the machine. And we'll come back to that later. There are two basic families of approaches to defining the meaning of a programming language. One is something called denotational semantics, which is due to Christopher Strachey and Dana Scott, and the other is operational semantics. And the operational approach, really, its origin lies in this paper by Gordon Plotkin, Call by Name, Call by Value, and the Lambda Calculus, which, among other things, talk about how you gave semantics to both call by name and call by value, and again, was talking about continuations, which we'll talk about here, and gave an appropriate semantics for them. So that came 3 years after the paper we're talking about. McCarthy's paper was 10 years before, and Landon's paper was 6 years before. Now, oh, and, oops, that's not what I want to do. Here's another paper of McCarthy's. The first paper describing LIST, Recursive Functions of Symbolic Expressions and Their Computation by Machine, Part 1. It was a paper so amazingly successful that there never was a Part 2. There was only a Part 1. Of course, I've put it up, A, because it's a great paper, but B, because it gives me a chance to steal from classic programmer paintings, which here is depicting McCarthy as Moses bringing down the tablets from Mount Sinai. And one reason I referred to classic programmer paintings is so I can brag that there's actually one about me. And I'm pleased to be able to say that propositions as types has actually been the subject of a couple of papers we love, seminars in I think both of them in the US, on different sides of it. So skipping over me, let's get to John Reynolds, because that's the exciting bit. So here's the paper we're talking about, Definitional Interpreters for Higher Order Programming Languages. It appeared in the ACM Annual Conference more or less as a tutorial in August of 1972. It was reprinted as a retrospective essentially 25 years later, actually 26, in Higher Order and Symbolic Computation. And then to accompany it, John Reynolds wrote a brief introduction, Definitional Interpreters Revisited. One of the things we're going to be talking about is continuations, and John Reynolds also wrote a wonderful history of all the many different times that the notion of continuations was independently discovered over a period of more than a decade. And I can highly recommend that paper as a supplement to what we're talking about. Are there any questions yet? Not yet, okay. But so there's this Q&A thing, which I'll just have a quick look at. Yeah, nothing really there yet. I think the best thing to do is that apparently there's a raise your hand icon, or you can just type in, I have a question. Just go ahead and put that in the stream, and with luck, I'll see it. I can only see about 2 things at a time, so I have to watch the stream carefully. Okay, this is the first page of Reynolds' paper, taken out of my library. I was handed this paper. We can look at the title. There's the close-up. So it's actually printed very poorly. So I had to, this is not my handwriting. This, I think, is Guy Steele's handwriting, because I got the copy from him. Somebody's asking if the papers are available easily and freely. And yes, that link to my blog post that is supposed to go up, which has just gone up, I carefully looked for links that were not behind paywalls. Right, so this is Guy Steele's handwriting, for those of you who know who Guy Steele is. He's also made almost as many important contributions as John Reynolds. He defined the scheme programming language. He's one of the people who first wrote down the formal definition of the Java programming language. And he's responsible for Common Lisp. He headed up the Common Lisp standardization effort. So I was a graduate student. I was lucky enough to have Guy Steele as one of my supervisors. And at this time, denotational semantics was a big deal. And basically, what denotational semantics was you wrote down an interpreter for your programming language in Lambda calculus. And then you said, this is the meaning of my programming language. Well, I was interested in functional languages, and what would that mean? That would mean you take Lambda calculus and write down the definition of its meaning in Lambda calculus. Are we really learning anything by doing this? So one question is, does this involve any ambiguity? If you define, so it was actually a thing at this point where you've got this great new programming language and you're all excited by it and happy, and you want to show off your great programming language. So you're going to write some programs in it. And naturally, one of the first things you do is you write an interpreter for your programming language in your programming language. And then you say, now it's very clear what the programming language means. But is it? Could you have a programming language written in itself that actually, there were two different consistent semantics that you could give it, where for each semantics, interpreting in itself would give a consistent result? So I asked that question of my supervisor, Guy Steele, and he handed me John Reynolds' paper, this paper, and said, read this. And I must have been in close to my last year of graduate school, but it was the techniques of this paper that I took with me and that have pretty much formed the basis of my research career, as well as the basis of the research career of pretty much anybody on the theoretical side of programming language design, and many people on the more practical side of programming language design. Here's the more nicely typeset version of the paper, right? The original version was just typed out on a typewriter. When it reappeared 25 years later, it was neatly typeset. But I'll be giving you excerpts from the version done on a typewriter. And there's Reynolds' introduction to his own paper. And right, you can see it began as a tutorial. In late 1971, Gene Samet and Bert Leavenworth asked Art Evans and me to give a tutorial session on the application of the Lambda calculus to programming languages at the 25th anniversary ACM National Conference. And then he goes on to explain why it was something that he did and Art did something, Art Evans did something complementary. And then here's the discovery of continuations, which again I recommend highly. And you notice how many different times it was discovered by Van Bijgaarten, Makursevich, Lockwood Morris, Chris Wadsworth, Jim Morris, who was a cousin of Lockwood Morris, M.J. Fisher, and S.K. Abdali. And Reynolds does not list himself as a discoverer. He wasn't, but he was sort of the first person who explained them in ways that people like me could understand. So let's dive in. So I'd forgotten, lots of the paper stuck with me for ever since I read it, which would, by the way, have been in 82, I guess, about a decade after it was written. Oh no, maybe 81. But many bits of the paper stuck with me, but not this bit. And this bit is really cool. So Reynolds begins motivating things by saying lots of people end up writing a definition of their programming language in their own programming language. And here he looks at 4 definitions. 2 of them, McCarthy's definition of list and Reynolds' own definition of his language, Gedanken, that appeared in the literature, and then 2 other similar ideas, the Morris-Wadsworth method, that refers to defining continuations, and the Sexty machine, which we mentioned was due to Landon, and then it he also refers to the Vienna definition language. So these are all places where people have written interpreters to explain the meaning of a programming language, often a self-interpreter. And then he breaks these up in two ways. Does the answer you get out depend on the order of application? I'll explain what that means in a minute. And does the interpreter written use higher order functions? So Gedanken, for instance, had a direct style interpreter. So it was an interpreter for Lambda calculus, but written using Lambda calculus. And indeed, the way that Lambda expressions were explained was using Lambda expressions. And it turns out when you do that, you can get two different interpretations that are both consistent. And this has to do with call by value and call by name. So call by value in Lambda calculus means when you're applying the function, first you normalize the argument as you evaluate the argument until you've got a value, and then you substitute that value in everywhere the formal parameter occurs. You've got an actual parameter, you evaluate the actual parameter, and you substitute it for the formal parameter. So this is the basic idea in Lambda calculus. Maybe I can even write it down. We'll see if this works. Oh, this is kind of painful. So lambda x dot, oh, dot doesn't work, dot n applied to v. That would reduce to every occurrence of x in n, replace it by v. I could write that out as well. That would be too slow and painful. This thing that I've just written out, if it's reasonably familiar to you and you're bored by me writing that out at such great length, could you please just type in a smiley? No smileys are appearing. Oh, there's a bunch of smileys. Okay, it's just slow. Okay, right, that's what I expected. Does anybody want to ask a question about this? I'm guessing most people would have seen something like this before, but if you've not, you should ask a question. Okay, so that's the basic thing. And here you notice I've written V to indicate that the actual argument has been reduced to a value. Now, I might have had here an arbitrary term, say M, and you could just substitute that arbitrary term everywhere. That seems kind of insane, but in call by need languages like Haskell, that's more or less what we do. It's just we use a common pointer to that term so that if it gets reduced one place, the benefit of that reduction is seen every place. Alonzo Church's original definition of lambda calculus used call by name, so he did not reduce the term before substituting it. But Barclay Rosser, when he wrote a review 2 years later of Church's original paper, said, you know, it might make more sense to reduce it to a value first. So all the way back, I think, to 1935, you already have the idea of both call by name and call by value. And then what Reynolds is referring to here when he says that it depends on order of application dependence. Yes, what he meant is if this interpreter that he wrote for Gedanken and Gedanken was run in a version of Gedanken that has call by value, it defines a version of Gedanken that is call by value. If you run it in an interpreter for Gedanken that is call by name, it defines Gedanken to be call by name. So you're not saying whether it's call by name or call by value. And it's ambiguous as to what you get. And then what he said, one of the points of this paper is if you write your interpreter in a different style, and a lot of what he was doing was making use of continuations to do that, then regardless of whether the underlying language is call by value or call by name, you get call by value. Later on in this paper of Plotkin that I mentioned, he shows how you essentially write definitions of programming languages using continuations, one of which it always gives you call by value, regardless of what the underlying interpreter is, and the other of which always gives you call by name, regardless of what the underlying interpreter is. So the cool thing that I hadn't remembered about all this was that he motivated it by referring to 1, 2, 3, 4, 5 different existing definitions and categorizing them. So grounding this theoretical work in a lot of things that were practically out there was a really brilliant idea. And then this becomes the outline of the paper. He begins by showing something in the style of a direct interpreter, which uses higher order functions to represent higher order functions and doesn't specify the evaluation order. Then he shows McCarthy's definition of list, which doesn't use higher order functions, but does define higher order functions in terms of other things. But again, doesn't specify the evaluation order. Because this will still use functions. If those functions are call by value, you get a call by value language. If it's call by name, you get a call by name language. It only uses first order functions. And then he showed how you could switch to using continuations so that you have specified the order of the evaluation. As I say, it's always call by value, regardless of what the underlying interpreter is. And then finally, he goes back and says, well, we wrote those in a first order way, but actually you can do it even more neatly in a higher order way. And this corresponds to Morris and Wadsworth's original definition of what's now called continuation passing style. So this became the outline of his paper. It had these 4 parts that went through these in turn. So then he goes through a long introduction explaining things which back then were quite unusual, right? He's writing in a functional language. Back then, most people had not heard of functional languages. So he had to introduce the basic ideas, most of which were taken from Landon's paper, The Next 700 Programming Languages, and Landon's language, iSwim. So one thing that you could do is define some mutually recursive functions. So x1 is the name of your first function, and its body is R1, and so on up to xn defines Rn. And the point is each of R1 through Rn could refer to the variables x1 through xn. So these are recursive function definitions. And then finally, all these definitions are available when you write the expression R sub d, which is the body of the let expression. And it comes in both recursive and non-recursive versions, but of course defining mutually recursive functions is a pretty important thing to be able to do. Any questions about that? Okay, let's move on. Ooh, what have we got here? So he goes on for quite a bit explaining the definitions in the programming language. I can't remember why I put up this page, sorry.
So, sorry to interrupt you, but there is one question. You can ignore the one from me. But Vladimir asked, how do you handle reading large Lambda terms? I presume it gets messy when you start encoding things like numbers.
How do you read large Lambda terms? The same way you read a large program. You've probably got skill at reading large programs. It's the same for Lambda terms. If you've ever read a Lisp program, of course, you know that you have to worry about parentheses piling up, and the same can happen with any large term. So having something where if you hover over closed parentheses, you can see the matching open parenthesis is helpful. But basically, it's just like reading any large program. Does that help, Josh? We'll go to the chat. You can.
I think it might. I wasn't actually the questioner.
Oh, sorry.
But it was helpful to me. It was Vladimir.
Oh, sorry. I've got. It's showing you for some reason.
That's because I marked that question answered when you started answering it.
Oh, I see. All right.
He says thanks.
Right. Okay. Good. There we go. Okay. Thanks. Right, but you're presuming Lisp at least has literals. Right, so pure Lambda calculus only has Lambda terms and nothing else. But as you can see already from what we have on the previous page, Landon's going to work on a variant, sorry, Landon and Reynolds both use a variant that has things like mutually recursive definitions. You know, you could define a lambda term as the Y combinator and write all this out that way, but that gets hard to read. So they are building more things into their programming language. They do have numbers. They have operations on numbers. They have mutually recursive definitions, and I think we'll see a couple of other things as we proceed. And he has this long introduction, and he's very careful to define everything. He even very carefully says, right, here are the different kinds of types I'm working with, and I'll always carefully use R to range over expressions, X, Y, and Z to range over variables. I think that's a curly L to range over lambda terms, A and B to range over values. I used V before. F to range over values that are functions. E and E prime to range over environments, and so on. So he very carefully defines his vocabulary. And then this is the ending of the beginning of the introduction to the programming language. And then, bam, a metacircular interpreter. And here it is, written out. And I think on the next page I've got it. So now we go into part one. Okay, so he begins actually by, you can see it at the top of the page just here. Let me underline it. Just here you can see he is giving some types. And let's look at that in more detail. So this is making use of what Landon called abstract syntax. What is an expression? Well, it's one of 6 things. It's a constant, it's a variable, it's an application of a function to an argument, it's a lambda abstraction, it's a conditional, an if then else, or it's a let rec, which is one of those let expressions we just looked at. So those 6 forms are the only forms that lambda expressions can take. And those constant here stands for things like numbers, or the plus operation would be a constant. So you'd have plus applied to 1, that's an application, and then you would apply that again to 2. What is an application? Well, it has 2 parts, an operator and an operand, both of which are expressions. What's a lambda expression? It has 2 parts. The variable, which he's called FP, so this is your bound variable, and then the body in which the variable may appear, which is your expression. So notice variables are just represented by things ranging over var, and similarly for constants. And then a conditional, right, has a premise, which is your condition, your conclusion. So this is an expression whose type had better return a Boolean. And then a conclusion and an alternative. You'll execute the conclusion if the Boolean is true, and the alternative if it's false. And then a let rec consists of, so here he's just got 1 rather than many with mutual recursion, which has a variable and a lambda expression, which is the function the variable is bound to, and then a body within which the definition is available. And again, this lambda expression might actually refer to this particular variable. So it's a recursive let binding. So that's a complete abstract definition of expressions. And then you evaluate an expression to give a value. What is a value? Well, a value is either going to be an integer or a Boolean or a functional value. And what's a functional value? It's a function that takes a value as an argument and returns a value as a result. So he's carefully written out types for all these things. He's got a static type system in mind, but the actual language he's defining, which is a simplified version of Gedanken or of ISWIM, is a dynamically typed language, right? Everything can just return something, and that might be either an integer, a Boolean, or a functional value, which again could take anything as an argument, either an integer, a Boolean, or another function, and similarly return anything as a value. So now we actually get the interpreter. Can people read that? Type a smiley if that's legible. Okay, lots of smileys going by. That's good. If it's not legible, then get better glasses or something, because I'm afraid I don't have any way of magnifying that. So here's our evaluator. It's going to take two arguments, R, which remember ranges over expressions, and E, which ranges over environments. And would we have a type for environments? Ooh, it's not showing here. It's just here at the top of this page. An environment is a mapping of variables to values. So it just says for each variable that's in scope, what value is it bound to? And if you evaluate an expression that may contain free variables, you need to know what the values of those free variables are. So that's what E tells us. So now we have conditionals written out in a nice concrete syntax, due more or less to McCarthy. So we have several Boolean valued functions here, right? So remember in the abstract syntax, we said, well, an expression is either a const, a var, an application, a lambda, a cond, or a letrec. He's got 6 functions, which are these names in lowercase followed by a question mark, which return true if the expression they're given satisfies, belongs to that disjunct. So we just look at the expression we're given. It will be one of these 6 things. Is it a constant? If so, okay, that's obvious. Just return the value of that constant. And evcon, I think, is not further specified, but just as things like, well, if it's plus, return the plus function, and so on. Is it a variable? If it's a variable, then we look up the value of that variable in the environment. The environment is just a function from variables to values. I'm hearing some pinging in my ears. Are other people getting that? I won't worry about it. No, other people are not hearing this pinging. I definitely am. I'm not sure what to do about that. This is getting bad. I wonder if it's a way of telling me that the battery in my headphones is about to die. Let me have a quick look.
We cannot presently hear you. I don't know if you know that. Still can't hear you. Oh no. Technical problems all around me. At any rate, while this gets sorted, the chat serves as entertainment and distraction.
Hello.
We can hear you. You sound great.
Fantastic. Okay. So the lesson there is not to use headphones that have a battery that's going to die. I mentioned at the beginning that it'll be interesting to learn about the technology. So I've just learned something important and painful. Okay, so we're back. Right, so we're in the middle of the interpreter. Right, so we're given an expression, an environment, we need to return a value. If the expression's a constant, there's a special function that returns its value. If it's a variable, just look that up in the environment, which we do by just, since the environment is just a function from variables to values, we can just apply the environment function to the given variable. If it's an application, then you evaluate the operator in the given environment, and you evaluate the operand in the given environment, and this should yield a value, which is a fun val, which remembers the functions from val to val. This should yield a val, and you just apply one to the other. So how do you implement application? With application. Right? This is why I was worried that maybe writing an interpreter to define the language doesn't tell you as much as you might need to know. Similarly, for a Lambda expression, what do you end up doing to evaluate that? You just evaluate, well, you invoke a function called ev lambda. So let's look at ev lambda. So you pass that both the Lambda expression and the environment. So here it takes two arguments, a Lambda expression L and an environment E. And remember, a Lambda expression is supposed to return a fun val, a function that given a value returns a value. So it accepts the value A, right? So its body is a function, so it's written as a Lambda expression. It accepts the value A, and then it evaluates the body of L in an environment that you get by adding one more thing. You extend that environment by saying, so it's the function that's just like this one, except first you check, and if your argument is the bound variable of the Lambda expression, then you return the value A, because A is the value that the bound variable becomes bound to. So we interpret an application with an application, and we interpret a Lambda with a Lambda expression. Ooh. And there, you see there are lots of underlines here. There's some underlining of if then else, so that's just saying this is a keyword. But there's this dotted underline here and this solid underline here, and we'll learn what those are for later. So here we're talking about extending the environment. How is that defined? It's very straightforward. It takes three things, a variable name, a value, and an environment. And what function is it? It's the one that, given a variable name x, if x is the same as z, return the value a, and otherwise look up x in the remaining environment. So again, that's a very straightforward way to define things. It's cleverly using functions to represent what's really just a list of identifier value pairs. So let's see, we're down through Lambda. Conditional. How do we interpret a conditional? With a conditional. So you evaluate the condition, the premise, in the given environment. And if it's true, then you evaluate the then branch, the conclusion of R in the given environment. And otherwise, you evaluate the else branch, the alternative of R in the given environment. And finally, how do you interpret a let rec? Well, we'll do a recursive binding. We're going to recursively bind the environment E prime. So we've got the given environment E. We're going to build a new environment E prime. And that's going to be a function, right? Because we represent environments as functions. So it's the function that takes x. It's very similar to extension. And if x is equal to the bound variable of the let rec, then we evaluate the body of the let rec in E prime. And that must be a lambda expression. So he's already simplified it in saying do an ev lambda rather than do an eval. Because if you do an eval, It's just this clause that'll be true, and it'll call f lambda. So he's just optimized slightly. And otherwise, right, so this is the environment, remember. So if x is down to if x is the bound variable, then return the body. And notice by calling f lambda, he's guaranteeing that we're returning a value here. And otherwise, just recursively, just return whatever x is bound to in the environment. And now that we've got our environment, we evaluate the body of the letrec in that new environment. That's the trickiest one. So notice we are 4 for 4. How is application defined? With application. How is lambda defined? With the lambda expression. How is con defined? With a conditional. How is letrec defined? With a letrec. And Reynolds coined a name for this. Right? He recognized this is sort of weird. And he coined a name for this, which we use to this day. He called such an interpreter metacircular, meaning that each interesting feature is defined in terms of itself. And notice that you still need to know things like what are the values of predefined things like successor or equal. And here he explains, okay, when you evaluate R, it should essentially be closed except for library functions, which are defined in the initial environment. And what is the initial environment? It's the one that binds successor to the successor function, which takes a value and returns its successor. The value must be a number, and the successor will be the number that's one greater. And equal is bound to the equality function, which takes 2 arguments, A and B, and returns true if they're equal to each other. So as usual, using what's called currying, all functions take just 1 argument. If you want a function of 2 arguments, you have a function of 1 argument that returns a function of the second argument. So you can represent functions of multiple arguments encoded with functions of a single argument in a fairly standard way. I know somebody's added another meaning of metacircular interpreter. It's a mind-exploding interpreter, which probably is a good way of thinking of it. Okay, so that's actually the basic idea, which is this is how you can write an interpreter. That's the first cool idea. So type a smiley if you're happy, or type into the text field a question if you're not. So also, I thought I'd step in. There's a couple of questions in Q&A. So if you wanted to just flip over there and read them at the top, or I could mediate. Yeah, why don't you read them out to me? Okay, so Ryan asks, he says, you call these types abstract, but they look similar to algebraic data types, the main difference being untagged unions. Is there a reason for calling them abstract? So that was a little bit ago, 13 minutes. Right, so you're quite right that what Reynolds and Landon called abstract syntax, not abstract data type, abstract syntax. An abstract data type is something different. The correct way to represent abstract syntax is with what we now call an algebraic data type. So the syntax that we use in languages like Haskell and standard ML to define these algebraic data types, that was first developed by Rod Burstall, who's a colleague of mine at Edinburgh, now retired. So the reason that Reynolds doesn't refer to algebraic data types is they haven't been invented yet. He's helping to invent them in writing this paper. Awesome. And then there was 2 people, well, one person asked a question, someone followed up. So John asked, is there a material difference between writing an interpreter for an AST in a pure functional language versus creating a denotational semantics, or are these the same thing? And Maximilian followed up and said he would say interpreter is operational semantics. What say you? You could view an interpreter either as an operational semantics or as a denotational semantics. And indeed, a simple interpreter like this one could be taken either as a denotational or an operational semantics. If you're going to take it as a denotational semantics, you then have to give your mathematical theory of lambda calculus that explains what's going on here. In fact, when people like Landon and Strachey started arguing in favor of lambda calculus as a way of giving meaning to programming languages, so you'd explain the meaning of a programming language by writing out something like this, Dana Scott objected. He said, well, I don't think lambda calculus is a good idea because it's just symbol manipulation. There's no actual mathematical model of what's going on. And Dana Scott thought this was a really bad idea. And he was sitting in the bath one night trying to say, you know, I bet I could prove this is a bad idea. Let me prove that there's no way of writing down a model of lambda calculus. And he's sitting in the bath trying to think of this when he suddenly goes, oh my God, because in trying to come up with a proof that there's no model, he realized that there was a model. And so he wrote that down. That was, I think, the D-infinity model. And that was the first mathematical model of lambda calculus. So half of denotational semantics is about writing out interpreters in this style. But the other half, the very important half, is about saying, yeah, but when you've written this term in lambda calculus, what does it mean? What is your mathematical model? Where types now become sets of things. What are they sets of? How do you represent a function as a set? And particularly a recursively defined function. And Scott provided answers for all that drew on ideas like continuity and topology. So I won't go into that in detail, but just to say there's some exciting mathematics that was going on in the denotational stuff. And so basically, if you think of this as something that you would then execute on a machine, then it is kind of an operational definition. But if you think of it as something that denotes a particular term, a particular point in one of these models, then you've got a denotational definition. So this can be the basis for either. And indeed, at the time Reynolds was writing, people were groping towards both denotational semantics and operational semantics. As I said, operational semantics came into its own 3 years later when Plotkin wrote call by value, call by name, and the lambda calculus. Okay, shall we go on? So here he's now explaining that in fact, when you've defined application using application and lambda expressions using lambda expressions, you end up having a language that's call by value if the underlying interpreter is call by value, and call by name if the underlying interpreter is call by name. Okay. So, sorry, no, there were 3 objections. Maybe I should review these. The metacircular interpreter does not shed much light on the nature of higher order functions. For this purpose, we would prefer an interpreter of a higher order defined language which was written in a first order defining language. In other words, he's admitting, that's point 1, he's admitting that if you explain application in terms of application and lambda abstraction in terms of lambda abstraction, maybe you haven't learned as much as you'd like. And then his second point, right, is that changing the order of application used in the defining language induces a similar change in the defined language. So that's the point we talked about before. And then his third point is we might want to introduce some form of jumps. And as far as it's known, you can't actually do that in a metacircular definition. So you might want something that's a better basis for defining things like jumps. And that's where continuations will come in. And then he says, okay, we're going to introduce transformations of our metacircular interpreter, which will meet, in fact, each of these in turn. Right. First, we're going to do one that meets the first objection, then one that meets the second objection, and the one that meets the second objection will, in fact, also deal with the third objection. It will be continuation-based and therefore easy for defining jumps. Okay, so the first step is, right, I have defined functions in terms of functions, higher order functions in terms of higher order functions. Can I write a definition that's only first order, so that I'm defining functions in terms of higher order functions in terms of first order functions? So I've defined something more complicated in terms of something simpler. And he called this defunctionalization, and to this day, that's the name that's used for it, and to this day there's active research on this topic. How do you transform systematically a definition from higher order to first order? So now he's going to introduce some more things, and the key thing to doing this is we're going to introduce a representation of a lambda expression called a closure. What this consists of is the lambda expression itself, so that is the bound variable and the body, and the environment. So we store the environment with the lambda expression. I guess most of you will be familiar with closure as the way you implement a higher order function. So this is one of the first places that was explained clearly. And what he's done here is he's gone through every place that something has appeared in, right, he's referring to different lines of the original Metacircular Interpreter where higher order things appeared, and he's giving representations for them. So all the other ones are concerned with the things bound in the initial environment. So we'll need a representation of the first function. So he says, okay, we'll call that SC. And then the second function, right, so these are all the underlying things. Let's go back and look at them. Right, so he's looking at this solid underline, and this solid underline, and this solid underline, and this solid underline. So there are 4 places where lambda expressions appear denoting values. And he said, okay, for each of these, we're going to replace that lambda expression with a first order value that represents it. So this one will be represented by a closure. And note, he's derived the idea of a closure very systematically. He says, okay, we just need something that represents all the free variables of this lambda expression. And there are just 2, right? A is bound. The only free variables that appear in it are L and E. Actually, let's underline this separately. L and E. So we have this one construct called closure that accepts 2 things, L and E. Here, there are, for the next one, sorry, and that deals with this underline. For the next underline, there are no free variables, so it's represented by a structure that has no arguments. This one similarly has no free variables, so it's represented by a structure with no free arguments. And finally, this one has 1 free variable. It's got A, which is bound immediately out here. But this underlined bit has 1 free variable, which is A. The outer underlined bit has no free variables. And so that he systematically has derived what we need to represent these, which is these 4 data structures, which we'll call closure, SC for successor, eq1 for equal with 1 argument, and eq2 for equal with 2 arguments, which has 1 thing, which is the first argument. And then how do we change saying eval, the body of L, to the extended environment where the bound variable is bound to A and the rest is the same as E? this is a line copied. This is the apply line copied from the Metacircular Interpreter. He says, we'll replace it by this. We'll define a new function called apply, which takes the function f and the value a to apply it to. And f should be a closure. And if f is a closure, then he's very systematic here. Let a, he's going to copy in this expression. He says, in this expression, how do we get a? Well, it's just the a we were given. How do we get L? That's the lambda part of f. Remember, f here is going to be a closure. And how do we get E? That's the environment part of the closure f. In, and then we just, this bit here is exactly the same as the underlined bit above. So he's just copied that from the original source verbatim. So he's very systematically transformed the source program to get rid of those 4 underlined bits. And then going back, you notice that we also use lambda expressions to represent environments, because an environment is itself represented as a function. Of course, you could just represent the environment as a list, right? It's a list of bound variable value pairs. So again, he's systematically, we've got, let's change my color here. We've got one, oops, I left one out. Right. 1, 2, 3, 4 things here that represent environments. And he's going to represent each of these, he's going to derive a systematic representation of each of these as well. And notice particularly, like the one up here, I'll just put some, extend the line a bit to draw your attention to it. That one was interesting because it's a recursive finding. So when he systematically derives the representation for those things, he'll systematically derive a way of dealing with recursion. So that's, so these first ones here are the ones we've already seen. And then he defines these as the representations of the dotted underline bits. And this last one, called rec, is the one that deals with recursion. It just consists of just the 2 free variables of that thing, which were the letrec expression and the old environment. And notice this one here, simp, that's rec. And this one here, simp, this is just how you'd expect to represent an environment as the bound variable, the value that it's bound, the bound variable, the value that it's bound to, and then your tail will be a pointer to the list that's the rest of the environment. Of course, you end it with this one, which stands for the empty list, or the empty environment. So it's all systematically derived by looking at the program. And doing all those systematic substitutions, you end up getting this program. So now, a lambda expression is represented. So now a lambda expression is represented by this make closure function. So make closure just returns one of those closure things that we saw. So when you define the data type closure, you get for free make closure, which creates one, as well as closure question mark, which is used here, which tells if you have a closure. So how do you apply something? You look at, if it's a closure, then you evaluate the body, as we saw before. But there were 3 other possibilities. It's the thing that stands for the successor function. Okay, then you just do the successor function. It's the first part of equality, which case you just build the second part of equality, right? So we have a make thing up here to make a closure. We have a make thing here to create an eq2. And if it is one of these eq2s, then you just do equality. Right, so each of these things was just read out, copied out from the corresponding part of the program. And then environments are dealt with in a very similar way. And in particular, rec here ends up building a closure that's going to refer to the same environment over again. So this implements recursion in a very straightforward way. A bit similar to having a bit of the list loop and point to itself, but instead of that, he's introduced a special item in the list, the rec item, that just stands for this thing that points to itself. So that's it. That's the key idea. And in a completely systematic way, he's gotten rid of all the higher order stuff. So are there any questions about that? Is anybody there?
Yeah, we're here. Sorry, I know that could be confusing. There were a couple of questions a little bit earlier. So Heath thinks that he heard you say D infinity model, but he doesn't think that's actually what you said. I have no idea how to actually get clarity on that.
Yeah, it's written as a boldface D into superscript infinity.
Oh, awesome. So it was, in fact, that. Okay. And then Levi said Birstall's paper that extends ISWIM with data structure definitions, and he just linked to it for people, so that's not actually a question. Sorry.
Okay, but that's a cool additional piece of information. And that wonderful paper by Birstall is one of the things that I could have put on my list of papers I love. And then here he's got I've copied this out of McCarthy's paper. This is McCarthy's self-interpreter for Lisp, which is essentially using the same techniques, but just done as a hack rather than derived in the systematic way that Reynolds did. But this is very similar in structure, just written in Lisp instead of in ISWIM. Actually, this interpreter for Lisp written in Lisp that McCarthy first wrote has a bug. And the bug is instead of binding the environment into the closure so that you get static binding, it uses dynamic binding. And it took, between 1960 when he wrote this paper, I was an undergraduate at Stanford in between 73 and 77. I was fortunate enough to learn Lisp from McCarthy. But I remember at that time, there were several technical reports discussing this thing called the funarg problem. And what the funarg problem was, we don't have static binding. And eventually, Scheme came along and said we should use static binding instead of dynamic binding. And then everybody had it right. The interesting thing is that the original Lambda calculus of Church had static binding. And McCarthy had actually sat in these classes of Church when you'll notice that the Lisp that's written here doesn't look like ordinary Lisp. It's got square brackets and arrows and semicolons rather than lots of parentheses. And this is something that McCarthy called M expressions. It was more like a traditional programming language. And then the data they acted on was S expressions. And one of McCarthy's students said, just as a hack to get things started, instead of implementing a parser for M expressions, could we just represent them as S expressions? And McCarthy said, yeah, okay, you can do that as a quick hack to get started, and we'll fix it later and add M expressions back in. And they never did. So they used S expressions to represent these things. But this is this is from his original paper before that hack. So he's written his M expressions, but has a bug, right? The bug is it uses dynamic binding. And still as late as the mid-70s, they were working this out. It was called the fun art problem. And eventually, I think in the late 70s, rather than the mid-70s, Scheme finally came along. That's right. I remember in my senior year, I finally saw a talk on Scheme by Hewitt, the person who defined it along with Guy Steele. Hewitt was Guy Steele's supervisor. And that was where I first heard various terms. But McCarthy had been a student of Church. And when one of the students said, oh, let's represent functions as S expressions, they needed a keyword for functions. And the one they picked was Lambda. And that was because McCarthy said, wait a minute, I've seen this before. And he went back to his notes and he realized that this was just like Lambda in Lambda calculus. And so he used the name Lambda. But he didn't study the notes carefully enough to realize that he should have used dynamic binding instead of static binding. And that kept everybody confused for another 15 years. Do we blame this on Church for not having explained things clearly enough, or on McCarthy for not having listened closely enough? I'll leave that to you to decide. Somebody said, do you mean static binding instead of dynamic? Maybe I mixed things up, but the original Lisp used dynamic binding, and then Scheme came in and used static binding, and we've generally used static binding ever since. Okay, so that's the first key transformation, is getting rid of higher order functions. But even though we've done everything in terms of first order functions, the interpreter that we've got there still has the property that if you run it in a call by value language, you get call by value. And if you execute it in a call by name language, you get call by name. So can we fix that? And Reynolds realized that you could fix it using this new idea that had just come up in the denotational semantics community called continuations. So we're going to do another systematic transformation on program 2. And so to prepare for this systematic transformation, he says, suppose we can divide the functions which may be applied by our program into serious functions, whose application may sometimes run on forever, and trivial functions, whose application will always terminate. So this turned out to be a very profound distinction between serious and trivial. And it has showed up ever since in various forms of both denotational and operational semantics as the distinction between values, where you've already got a value in your hand, which correspond to as trivial functions. So a trivial function always returns a value. But a serious function, the trivial one always returns a value. A serious one returns what we now call a computation, which may not terminate. So we have the distinction between trivial things or values and serious things or computations. And that distinction has remained with us to this day, and among other things, shows up in monads, in Haskell and many other languages, where the normal values in the language correspond to values and the monads correspond to computations. Okay, and then it goes on. As can be seen with little thought, the condition implies that whenever some function calls a serious function, the calling function must return the same result as the called function without performing any further computation. In other words, it must be a tail call. But any function which calls a serious function must be serious itself. Thus, by induction, as soon as any serious function returns a result, every function must immediately return the same result, which must therefore be the final result of the entire program. Now, if your head has not been exploded by anything you've seen so far, that probably exploded it. And you're probably feeling very guilty because I've just got some confirmation from the audience. You're probably feeling guilty because he began this difficult paragraph by saying, as can be seen with a little thought, which makes it seem like, okay, this is so trivial and obvious. If you read his introduction to the paper written 25 years later, he says, well, where I said, as can be seen with a little thought, the thing that immediately applies it isn't actually true. And so he regrets having used the phrase, as can be seen with a little thought. He says the condition implies a certain thing. In fact, it's the other way around. The certain thing implies the condition. And so he said, I can't remember what the condition was. No, I can't either. Let's leave that out for a moment. But the notion is that we're going to represent serious things must always be implemented with tail calls. So here's what we're going to do. We're going to give each function that's serious an additional argument. So if the old function, right, you're going to apply the function and then do something, C, to the result. But now we're not allowed to do anything except once we've applied the last thing other than just return. So he's going to use a trick. He's going to say, okay, we've got a function. It takes all those arguments as before, x1 to xn, and one more argument, C. C stands for continuation. So instead of saying, okay, you run, you return, and then you do some more stuff, it just says, you run, but one of your arguments is what you should do after you've done your main thing, and that's C. And in this way, he's going to, you'll see that the third interpreter that we write, which will be derived by systematically transforming the second one, has the desired property that all the calls are tail calls for the serious functions. So I'm going to speed up a little bit because we've been going for close to an hour and a half. I want to finish before we've reached an hour and a half. So I'm going to skip over some of the details here. It gets a little bit more complicated. But essentially, this is the basic idea. So as before, he introduces representations for all the different data structures you've got. And then he rewrites the interpreter, and you can see that all the serious functions, which are going to be eval and apply, and apply applies a function to an argument, and then continuation applies the continuation to a given value. So he's going to represent continuations also as these first order terms, and that's what this is. He went through and worked out, okay, these are all the places we're going to need something to represent a continuation. So rather than using a higher order function, we'll represent it in this way. And then everything works out. You notice that, I'm going to go back for a minute. If we go back to the original outline of the paper, here we are. Right, we started with a metacircular interpreter. We got rid of the higher order, we started at 1 with the metacircular interpreter. Then we go to 2, which is we do defunctionalization to represent all the functional terms with new data structures. And then he slips down to 3 and says, right, we're still going to represent all our functions as data structures. So now he needs to introduce data structures for all the continuations. It might actually have been simpler if he did part 4 before part 3, right? You'd have to undo the changes of 2, go back to 1, and just change everything to be use continuation passing style. So what he does is first painfully represents all the continuations as these data structures, and then goes back and gets rid of them, so you can see directly the connection to 1. It might actually have been better if you went 1, 2, 4, 3, just left to right, top to bottom, rather than in this funny loop. But hey, it's a great paper anyway. So 3, he uses defunctionalization and continuation passing style. And then finally, he undoes that and shows you what it looks like with higher order functions in just continuation passing style, which you can see is much more compact. And now you can see that the last thing that eval always does is it calls C, passing it the value of expression R in environment E. Indeed, under var, that's completely clear. And that's what happens with all the others. And then ev lambda, a lambda expression now, takes not just a value, but again, an additional argument, C, which is the continuation, which once the lambda expression has worked out what its value is on the argument A, it then passes that to C. And does that by calling eval, where the arguments to eval are the body of the lambda expression, the extended environment, and that continuation C that was passed into it. Is everybody's head suitably exploded? I hope so. This is a very nice way of writing interpreters, and then he goes on to show that, in fact, we can write other things that let us get hold of that continuation, and this is what became the call with current continuation operator of scheme. It was originally called an escape expression in Landon's SECD machine. So the SECD machine had a way of executing escape expressions, and I just thought, that's a hack. That's an artifact of the way the machine is defined. And it was only when I read Reynolds' paper, where he explains these things not in terms of the SECD machine, but as this sequence of interpreters, that I suddenly went, oh, it pops up by a very systematic consideration of this very obvious metacircular interpreter. Oh, it's not a hack, it's an idea. And this was the first time that I understood that there was something useful and interesting about continuation, about the escape operator, and about continuations. So Landon invented it, but I didn't believe it when I read Landon describing it. It was Reynolds that made me believe it. So coming up with ideas is important. Explaining ideas so that other people can understand them can be just as important. And then here's his definition of how escape expressions work. Right, so somebody, I noticed in the stream that somebody's asking about continuations and call by value. When you have written out the compiler in the interpreter in this form, it is now the case that you never it's getting late. It's going to be hard for me to explain this clearly. But it's structured in such a way, thanks to this distinction between trivial and serious. The trivial things will terminate anyway. So if it's trivial, there's no difference between call by value and call by name, because they only differ if you get into an infinite loop. Otherwise, they'll both return the same value. So it's only the serious expressions you care about. And for every serious expression, it's always implemented by passing what's guaranteed to be a value, because it's only applications of trivial functions, to the continuation. And hence, everything's always evaluated to a value before it's passed to the continuation. And the semantics you get is call by value. There's a different translation he could have done that would have always given him call by name. And if you want to see those two different translations boiled to their essence and explained even more clearly, have a look at Plotkin's call by name, call by value, and the Lambda calculus. He went on and then said, well, what if we had side effects, like a store that we could assign things to, and he updated his interpreter to include side effects, but we don't care about side effects, so we'll leave that out. Right, we've reached the end, for which I'm rewarding you with another picture of John Reynolds. You may now all type applause into your text interface, I guess. Slow, so nothing's happening. And then after that, we can have some questions. Are there any questions, Josh?
Sorry, I was muted. So there was so Ryan sort of followed up his earlier discussion about algebraic data types, and he said, okay, so following up on my earlier question, the predicates effectively make these tagged unions and thus algebraic data types.
Sorry,
which is,
I was just noticing that I'd not seen any applause in the stream, but it was because I was looking at the wrong place. There is some applause, yay. Thank you, guys. Sorry, could you just read the question again?
Sure. So Ryan, who previously asked the question about abstract or algebraic data types, said, okay, following up on my earlier question, the predicates effectively make these tagged unions and thus algebraic data types.
Correct. Yeah, I mean, if Reynolds is using a more complicated thing because it involves disjoint unions, and you might ask, why is he doing that? Why? Sorry, he's using, unions that may or may not be disjoint, but in fact, the way he's using them in practice, they're always disjoint. So why doesn't he just use disjoint union, which is an easier thing to implement, as the basis for what he's doing? And the answer was, it was early days. People hadn't yet gotten to the point of realizing, oh, we should just define and use algebraic data types, which are a subset of all the things you could define this way. He was just using ordinary set theory in a certain disciplined way that later was recognized to be algebraic data types. So he would have used algebraic data types if they'd been invented yet. Instead, he sort of got 3/4 of the way to inventing them.
Okay. I don't see any other questions. If you have a question, just plop it in chat.
So Ryan's great for asking questions. Come on, guys. I want more questions.
Oh, so I had one.
I'll think I did horrible talk because nobody understood enough to ask a good question about it.
So I left one for the end that I wanted to ask. So you said that this paper formed like the foundation, I think you said, of your research career, and I was just curious which one would you say comes in second?
Oh, for forming a foundation for my research career?
Yes.
Probably the one you've heard me refer to a lot, call by value, call by name, and the Lambda calculus.
Okay. Awesome, thank you. And Ryan asked another one. He said the environment was defined as a linked list. Was this motivated anywhere?
Yes, it was motivated. If you go through and read the whole paper, at the point where Reynolds is applying his systematic technique to get a representation of continuations, he explains exactly what I said in the talk about this corresponding to essentially using the ordinary linked list representation of an environment. And then somebody says, does anyone know a version of this paper with modern Haskell syntax? No, but if you look closely, you'll realize that the language that Reynolds used is very similar to Haskell. That there are not many significant differences. I know it can be a little bit hard to read a slightly unfamiliar language, but hey, I bet you've read some JavaScript at some point in your life. If you can read that, you can certainly read the version of Gedanken used in this paper. Oh, and somebody's suggesting doing a translation of all the code in Reynolds' paper into Haskell and posting it, and I think that's a brilliant idea. Yes, when you do that, please send me a link. I think that'd be great. So it sounds like one really useful piece of work will come out of this talk, which is fantastic. Thank you, audience.
Jean-Philippe asked, what does this paper still not explain about the Lambda calculus? Does Reynolds have a blind spot?
Well, it doesn't tackle the existence of mathematical models of Lambda calculus, which is what Dana Scott tackled with Denotational Semantics. I mean, there's lots of great stuff in this paper, but Lambda calculus is a much, much bigger subject than that. So, of course, there are many interesting things that Reynolds doesn't touch upon. It's a great paper, but there's still plenty left to do afterwards. Indeed, it's set the foundation for, so 72, that's getting close to 50 years ago. But it really did have, I can confidently predict that when you look back in history, you will see that that paper set the research agenda for the next half century of work on programming languages and Lambda calculus.
Okay, so Heath has a couple of questions. I like the first one. He asked. He says it's a silly question, but how do you think this is related to any of the work on session types?
The way in which this work relates to the work that I've done on session types is that the work that Reynolds did was much more foundational and much more important.
Okay, and then Heath asked one more question. He said, when are you going to make a BBC documentary based on the history of Haskell paper?
I think you have to ask the BBC that, not me.
I'm sure he will. Okay, any other questions? Going once, going twice. I think there's been plenty of time to ask them if they were there. Okay, well, do you have any closing remarks you wanted to say? Not like you haven't been talking.
When I started, I'd hoped to get through this in about an hour. It took me an hour and a half. So I just want to thank everybody again for showing up, for giving me a chance to learn how crap I am with technology and to maybe be a bit better with it next time. I want to apologize for going a half hour over, and thank you for your patience in staying. And Lambda calculus and programming languages and John Reynolds are great. Go out there, learn more, and enjoy.
Okay. Well, thank you very much, and thanks everybody for coming. This was, for what it's worth, I would have stuck around for another 30 minutes. Anyway, so we will do this again next month. We don't have a speaker yet, so if you can think of anyone that we should ask to speak, that goes for you too, Mr. Wadler, then just let me know and I will badger them. Sometimes I have to help them make shirts to get them to talk. Just kidding. Anyway, so yeah, that's about it. Once again, thanks to Big Marker and Hired and Remote Meetup and Daily Drip, which is me, which is a little meta. Anyway, so I will now turn off my webcam and y'all are free to hang around in the chat as long as you want. Thanks.
Okay, thank you, Josh. Thank you, everybody else. Good night.